Okay. I will first make the introduction in Chinese. Okay. I believe today's lecture, okay, will be in English, and so the introduction first I will use the Chinese. And 大家都知道，今年这个诺贝尔奖是跟这个希格斯这个粒子相关的。那在10多年前，这个台大物理系就是说能够参与这个就是说这个大强子对撞机 LHC 的这个 CCMS 的实验，是当初这个侯维硕老师等于是做 proposal 带着大家参与的。那10多年来，当然有很多的这个进展。那当然去年的这个希格斯粒子的这个发现，是一个很重要的一个里程碑。那因此今天当然我们非常高兴，就是说能够请到这个侯维硕老师啊，来跟我们这个谈谈这个希格斯的故事啊。当然这个希格斯故事 Higgs Story 的话，应该是不只是就是说告诉大家希格斯这个机制是什么，那以及当初的历史啊，怎么 propose， 怎么就是说希格斯怎么就是说提出来这个粒子的这个概念，然后以及到现在我们能够就是说经过这么多年能够找到这个希格斯粒子的这些故事。那侯老师1980年在台大物理系毕业，那之后到美国的话是这个 UCLA 的物理系，拿到这个博士，1985年，然后他在美国跟欧洲从这个博士后到这个就是说这个博士等于是研究员嘛，大概晃荡了7年，好像那个包括这个 Max Planck Institute 在这个德国的，还有这个瑞士的 PSR， 1992年回到台大任教。那目前当然侯老师已经是台大的这个特聘教授，而且过去他也得过几个非常重要的奖项，有教育部的这个学术研究奖，还有这个教育部的讲座教授，现在也是台大讲座教授。好，那侯老师当然在过去这么多年做了相当多的这个就是属于这个粒子物理跟高能物理的推动。那现在也是在这个国科会跟台大，一个是麦鼎，一个是拔尖这个计划的这个主持。好，我们现在欢迎这个侯老师。
Thanks for the introduction. 谢谢熊老师的介绍。Okay, let me switch to English. The start of the Higgs story is this slide. A few weeks ago at the Colloquium lunch, the organizer, Professor Junwei Chen, said that a slot is reserved in October because of the Nobel Prize. And then I joked, I have a picture with Peter Higgs himself. Does that qualify me? And then Bob said, oh, you have it on your door too. So that explains why we are, Bob and I are here today. We got a little bit stuck. So I should have put a credit here. This is not taken with my own photo, my own camera, but with a camera of Professor Guo Jiaming of NTU. This was taken this July in Stockholm, of all the places, okay? So me, happily, with Peter Higgs. End of the talk. Oh, no.
我先问一个小问题，你是我们这个物理系英文最好的老师之一了。那你的 title A 为什么用小写而不是用大写？
Okay. The person who asked the question is my teacher at NTU. So this is a planted question. I will explain it. Okay.
So why small a?
Yeah, it will be explained. So this is the Higgs story. I think I and Bob and a few others actually watched the show online And this is a screenshot. So to guide your eye, it's about the theoretical discovery. It's about the origin of mass. Very big stuff, okay? And furthermore, actually, this is unusually long. If you look at 3 lines from the Nobel Committee, very unusual, because they explicitly say, according to Bob, this disqualifies Atlas and CMS in getting the prize. By the Atlas and CMS experiments at CERN's Large Hadron Collider of a recent discovery of predicted fundamental particle. Okay? So therefore, Atlas and CMS, this is a public web page, it's still there, that we acknowledge, we congratulate the 2 newly minted Nobel laureates. This picture itself was taken during the July 4th announcement a year ago of Peter Higgs and Francois Anglais talking with each other. And I don't know whether it's a consolation or not. In fact, Atlas and CMS collaborations received the EPS HEP prize in the July meeting of the EPS HEP Society. Since I'm a member of the CMS collaboration, and as Bob mentioned, I'm coordinating the NTU NTU activity. Okay. Anglais. I should have read. Maybe I go back. I think it's something I glossed over. Okay, let's read. Université Libre de Bruxelles, Belgium. Okay, that's my fake French. Anyway, the thing is, some of us, at least 6 people, during lunch had some Belgian beer. So if you hear some snoring, including my own, you know where that's coming from. Okay, we had a toast with Belgian beer. Okay, that also explains my slip in English. So it's me too, because the 2 big experimental collaborations received this prize. It's a little bit unusual, but there are 3 named persons, which are the first 3 spokespersons.
It's 2 CMS, 1
Yeah, right. Ida Yenny is the earliest spokesperson of Atlas, and the 2 other were the spokespersons of CMS before the discovery. But Braut, Anglais, and Higgs received the prize in '97, so that's not really a big deal, but I'm happy about it. So this is still the unfolding Higgs story, okay? So July 4th, who are the 3 persons here? The 3 named, in a certain sense, in the Nobel announcement: the CERN Director General, the CMS spokesperson who announced it, and the Atlas spokesperson who announced it last year. This is courtesy Hitoshi Murayama, which he likes to show this slide because it was announced on July 4th, so he called it Higgs Dependence Day. But notice, well, it was announced last year, not just this past July 4th, but a year ago. So clearly the prize was not given a year ago, roughly because I think it was post-deadline. So now I start to explain a Higgs story, okay? So something funny happened at March meeting up in the Italian Alps this year. Dmitry Denisov is an experimentalist at Fermi Lab, had a statement like this. These are verbatim quotes, okay? Higgs-like is now Higgs, renamed during this Marvion QCD workshop. And that was in March, and echoed by Michelangelo Mangano of CERN. Let me not read this, but just saying that this is a Higgs, okay? And it was further echoed, I must say, probably controlled at CERN, because CERN had a post and a press release around middle of March saying that new results indicate that new particle is a Higgs it smells to me that CERN wants to be for sure. I suspect that, okay, this I didn't put in very clear wording. I suspect that a short list has to be formed by March. And changing from Higgs-like to A Higgs probably was very important, okay? So that's why I planted the word A Higgstory, okay?
But they still use the word indicate.
Huh?
Indicate mean does not imply 100%. Indicate.
Professor Yang, your English is very good. Okay, let's go on from here. So that's the Higgs story. The Higgs story, but I have a lot of wordplay here. So you can see it here. I have a lot of history here because, damn it, it took 50 years. And if you look at Angle and Peter Higgs' photograph, yeah, okay, we'll get to that. The other thing is that I could have put this GG in parentheses because the discovery, as far as we can tell, is made through colliding two gluons. So it's a history also of the gluon-gluon production and detection. Okay, part of my mission today, in fact, is to try to bridge the gap that we find sometimes in our faculty meetings between particles and field and condensed matter physics. Okay? Okay, so the main part is in the color code here. Well, it's not very clear in this color code. The history of the Higgs mechanism is the main part of this talk, and plus other things. So there we go. I want to start with two little things. One thing is our common heritage, starting with prehistory. By prehistory, I mean back at the end of the 19th century towards the beginning of the 20th century. So J.J. Thomson discovered the electron for us. Becquerel discovered radioactivity, both in 1896. And it took the young Rutherford at that time to distinguish that radioactivity had three kinds: alpha, beta, and gamma. Everybody knows this. Now the special thing about Rutherford, and let me remark, saying that people may think, my other counterpart, my not just condensed matter people, but non-particle physicists, even particle physicists, may view our alpha ray as nuclear physics or particle physics. But you must give thanks to Rutherford's mastery of the alpha rays, because the nature gift of alpha rays at a few MeV kinetic energy led Rutherford to probe and unravel the atom. Nobody had ever done that. The atom had a core. The atom had a nucleus. So this is a true common heritage, because after that, though this is Rutherford's picture, could explain why this picture will hold, that's a quantum error, okay? Now, gamma ray is more boring. It's really like a nucleus that Rutherford discovered. If you shake it, it can emit photons. But emitting electrons was pretty mysterious. So I just give this kind of a picture here that starting from Becquerel and Rutherford, and I'll explain this picture towards the very end, the start of weak interaction, okay? Because that turns out to be actual theme of today's talk. But this is our common heritage. You may think alpha and beta rays are old stuff, but we have to be thankful of the alpha decay. The beta decay is part of particle physics now. So one other thing special about 1911 is that Kamerlingh Onnes discovered superconductivity. Remember this old guy. Look at this here. It's not so different. Okay, the picture is not so clear now. But he's a low temperature guru. Okay, so there are low temperature people here, I imagine. And the next prehistory I want to turn to is superconductivity. This is a slide I stole from a web page of let's say 6 years ago, about the 50th anniversary of the BCS theory. Okay. So this is the title of the paper. The three famous authors, Bardeen, Cooper, and Schrieffer. So I think it's worth reading. This is from their webpage. So as John Bardeen was heading to Stockholm to pick up his first transistor Nobel Prize, he told young student Bob Schrieffer, work harder. I want results, okay? Anyway, the rest is history. So I also introduced this word, the triumph of BCS is a triumph of squalid state physics. Now squalid is a nice way to say very bad things, okay? So this way of calling, you know, my dear friends, what they do, comes from Gilman. So you can see around this time, 1957, particle physics and condensed matter physics has really parted their ways. Okay? I say 1950 as this prehistory year is that BCS theory can be put into a simpler form, so-called Ginzburg-Landau theory. If you're familiar with it, in statistical mechanics and phase transitions, they invented an order parameter, and the order parameter is a precursor of the Cooper pair. So you'll see this kind of a language or thought permeating through this talk. Okay, these are my true colors. Most of my life, I've been working with flavor physics and CP violation. So I was happy for these two gentlemen receiving the prize. I was also happy taking part in the Spell experiment, which helped these two people get this prize. So this is the second time for the Anglais Higgs Prize. But today, for that prize, I want to talk about Nambu. Read the words here, spontaneous broken symmetry. Shorthand is SSB. So I'm now going to go on and say that Nambu was the guy who really bridged between particle physics and condensed matter physics. And well-deservingly, he received, very belatedly, a Nobel Prize for it. So I don't know what I missed, but these are the original talks. So something may have changed, but whether Nambu likes it or regrets it, you know, these are public domain. So these, I'll quote a few slides from Nambu's 2008 Nobel lecture. He actually didn't go, but that's another story. So I box here, my early exposure to condensed matter physics benefited me. Now this is too long to read, but basically it says, you know, I went to NTU, but the particle physics professors were not so good, but condensed matter people were not bad, so I picked up some condensed matter, okay? Okay, so after he received his Doctor of Science, a few years later he went to Chicago. He went to the US and ended up Chicago. So this we might as well read. Anyway, this is from his autobiography and his collected works. So here's about the BCS connection to gauge invariance and spontaneous symmetry gradient. By the way, the thing is, in the 50s, for normal physicists, broken symmetry is not a new thing. Okay, but for Nambu was still a little bit new. So let's read this part. One day before the BCS paper, Bob Schrieffer, a student, came from Illinois to Chicago to give a talk. So Nambu says, I was very disturbed. Their wave function is not gauge invariant, and that's sacrosanct. Okay. So it didn't make sense, but Bardeen had received a Nobel Prize, so it was very impressive. So he took notes. So he tried to understand the problem, and 2 years later, he finally wrote a paper with this title. So putting together gauge invariance and the connection with superconductivity. Okay, don't worry. I'm not going to teach you really gauge invariance here. Okay, something may come out, but this is a colloquium. Here I just want to quote that he found basically zero mass modes, or what we call zero modes. And he nicely thanked Schrieffer on this work that took 2 years. And I think in '59, Bob Schrieffer actually went to Chicago as assistant professor for a year. Okay, so this is really what I said, a bridge between particle physics and squalid state physics. Okay, so still quoting from Nambu, this is part of planting in things that hopefully will look more familiar as we go on. So we already mentioned the word Higgs mechanism, Nambu-Goldstone boson, and we saw from the previous page, Nambu said that the BCS theory is not gauge-invariant. What is going on? This page will be very dense, but for a purpose or because of the quote. So there are Nambu-Goldstone bosons. They are massless. What are they? This Mexican hat, I will not explain it here. But he said, if you look at this Mexican hat, if you push a marble around that hat's rim, there's no resistance. So there's no inertia, there's no mass. Not this mode. Okay, we'll come back to that. So this, the first noticed by Nambu, and then picked up by Goldstone, and the grand proof in relativistic Lorentz invariant field theory, theory settings, is by Goldstone, Salon, and Weinberg. It's called the Goldstone theorem, and the appearance of Nambu-Goldstone boson, massless objects coming from this symmetry breaking. Okay, don't worry if you don't understand this page, because there's more to come. He doesn't mention Meissner effect, but I put it here, and this this plasmon at this state mixes with a gauge boson, the photon, and becomes the plasmon. This is already the Higgs mechanism, and this is the distillation of his Nobel lecture in 2008. So he mentions Anderson, Angley and Brown, Higgs, Voronek, Hagen, and Kibble. So these were the contenders for a potential prize for the Higgs mechanism. And I've already marked in colors who were the picked winners. Now there's a funny name here now, Brouts, in black, underlined. I'll get back to this, okay? So you can read this in Nambu's lecture. Anderson's stuff is non-relativistic. Never proven relativistic. He made a, I'll get back to this, don't worry. And luckily, Anderson received his own prize in regular condensed matter physics in 1977. So that seemed to have pacified him. Now this, I put a, a bracket here. Oh, this is another comment which I will not dwell into, but Nambu says that what Angley and Brown and what Higgs does is really a Ginzburg-Landau version in analogy with the BCS theory. It's an overtone that it's not a true theory, okay? But that's not the main theme today. The reason I put the last three gentlemen behind a bracket is because in 2004, that was before the prize of 2008, the Wolf Prize, one of the precursors for the Nobel Prize. As I said, this page is very dense. Next, I'm going to go through this, hopefully to let you understand better. But in a nutshell, roughly, I should have more to say quoting from my book. This is a funny page. So this is what I call Nambu's comment on the Higgs mechanism. This is his Nobel Prize acceptance speech. He has received the Nobel Prize for spontaneous symmetry breaking. But he laments, I thought the plasma and the Meissner effect had already established it. I think he was here referring to Anderson and what followed. But Brown and Angley in particular, but curiously not Higgs, although Higgs amends in his talks later, they clearly referred back to Nambu's original insight in connection with BCS as the starting point of their studies. So this is part of the amendments that Higgs made. He says, yeah, it surely started all with Nambu in 1960, and so on and so forth. I will not truly explain this here, but the left-hand side, Fermi surface, Fermi statistics, Fermi C, and so on, that's coming from the non-relativistic backdrop. and the Dirac particle, Dirac-C, in the end, the Fermi-Dirac statistics, again, becomes our common heritage. And I will not explain the mass gap here. No, that deserves another talk. But some of you may be familiar of this kind of a gap.
So when was this? Higgs.
What?
This handwriting.
I would say maybe late 2000s, when he started to be invited to talk about how he discovered what he discovered. Okay, but as I said, this is artwork from Peter Higgs himself. Now here, if you look at the notation that Peter Higgs put down, this order parameter, this Ginzburg-Landau field, called phi, is made equal to a psi bar psi. That's sort of a particle anti-particle pair, and referred to as Nambu's model because I will not introduce it here, but Nambu, miraculously, totally brilliantly sees through the clouds and explain roughly how the proton got its mass. We're not going to get into that part today. In contrast to this psi bar psi, for the BCS theory, everybody knows it, group of pair and so on, electron-electron talk with each other through exchanging of phonons, is really a particle-particle pair dancing together. So the order parameter which condenses in the BCS spontaneous entry breaking, the condensate, is different from the one that, but Nambu got his inspirations there. Okay, now I'm going to turn to the Meissner effect, because I mentioned it twice now. Now I play a joke. What is the Meissner effect? It's the effect due to Mr. Meissner. Got it? Okay, that's not very good. They're not satisfied. The Meissner effect is kind of a maglev phenomenon. You have a piece of superconductor, then a magnet, well, but not a very heavy one, can float above it. So this is the Shanghai maglev train. Then the professor is unhappy. What is the Meissner effect? Okay? Oh, sorry. Before that, just a clip. This is this picture here uses liquid nitrogen, so that's a piece of high TC superconductor. Okay. Okay. As I said, professor is unhappy. What is the Meissner effect? Then you say, oh, magnetic field cannot penetrate a superconductor. Okay. The professor says, I'm happier now. But explain more. What does it mean? What it means is this London penetration depth and attenuation of the magnetic field is a skin depth. And magnetic field starts from outside and disappears inside the superconductor. So this attenuation in a physical length, this London penetration depth, can be interpreted as the photon effectively propagates with a mass inside the material. By the way, this is the Higgs mechanism. So a second ending to the talk, because the Higgs mechanism has been explained, okay? So you see, Meissner never understood this, but the phenomena that he uncovered is relevant to the talk today. Okay. Okay. In that condensed slide, I said, okay, we know the winner, Anglais and Higgs. There's a third name that I put in black. The only guy put in black is Robert Brown. So unfortunately, he died 2 years ago. So this we can roughly read. He was born in New York City. Became faculty of Cornell at age 25. His major was more like phase transitions. So in fact, Anglais was his postdoc at Cornell at 59. You can imagine what Anglais was doing at that time. Okay? And the interesting thing is, they became kind of brothers. So when Anglais returned to Brussels, Brown actually resigned from his post from Cornell, okay, and moved to Brussels. Became a professor there, and held Belgian citizenship later on. Now, this is really a tribute to Robert Brown. By the way, this explains why people call